Alright, so hello everyone. Welcome to Chapter 8 of Chemical Structure and Reactivity. So this by me. And in addition, here's the shout out list including everyone that has supported these lectures. If you want to be added to the shout out list, just send a message in Lectureland. I'll add you to the list for the next chapter, alright? Without further ado, let's get into this chapter. We covered last time in Chapter 7 about thermodynamics. I know it's not on the slide, but last time, we mainly covered things like thermodynamics, and especially at the start of this book, like molecular orbital theory, electrons and atoms, basic bonding. With all these concepts, we're going to use these concepts from like chapters 1, chapter 2, chapter 4, and we're going to use these concepts in order to gain understanding of bonding within elements. So we're talking about like metallic bonding, the structures of certain elements, things like that. So that's what we're mainly going to cover in this chapter, and I do have the overview right here. At first, we'll go over electron configurations and effective nuclear charges in this chapter. Then we'll talk about the various sizes that atoms can have across the periodic table. Now, from the knowledge that we've learned so far in this book, such as some thermodynamics, we will then learn about ionization energies and electron affinities. Now, in addition, we'll also talk about oxidation states, but only for a very brief moment. And finally, we will be talking about bonding in the elements, and where to move forward with the next chapter on bonding between the elements. So here are the overall key points of the chapter. So, the first key point that I want you guys to know is that the energies and sizes of atomic orbitals vary across the periodic table. And if you understand the sizes and the energies of these atomic orbitals, you can rationalize why bonding in the elements are the way that they are, because of the energies and sizes of atomic orbitals. This will also be useful for the next chapter. And in addition, understanding effective nuclear charge and also the concept of screening will help us understand these bonding trends additionally. So that's a nice little addition, along with actually understanding sizes of atomic orbitals and the energies of these atomic orbitals. And then we'll go over some more effective nuclear charge lore, and we'll go over things like ionization energies and electron affinities. Now, our second part of key points is here's the especially big one. If we're talking about bonding in the elements, the second period is sort of an anomaly compared to all the other periods. So that is something that we'll need to investigate in this chapter to actually understand this entire periodic table. And then we'll talk about how the structures adopted by the elements, we can rationalize that by thinking, what are the valence electrons available per atom, and what are the size of the orbitals? And finally, we'll top this chapter off with considering how structures of metals can be thought of as simple ways to stack spheres together. So we're going to go over the periodic table at first. So, as you know from high school chemistry, Dmitri Mendeleev developed the periodic table, and he grouped elements in this table based on atomic masses and the properties of elements. Now, we know that we're supposed to arrange elements based on their atomic number, which is of course the number of protons within the nucleus. And in addition, we also have to consider the various arrangement of electrons in shells. Generally, if you want to determine many of the chemical and physical properties of an element, you have to consider the valence electrons, because those are the electrons that are mainly going to be involved in bonding and interactions. Here's a quick image of the periodic table. So as you can see, it shows your valence electron configuration, it shows the atomic number, and in addition, it also depicts some elements such as polonium, nobelium, technetium as yellow. That yellow color just means that they're radioactive. And in addition, you can see that these valence electronic configurations have different colors. As you can see, one's kind of blue, one is kind of, I say, like greenish. Now, the main reason we do that green color on the electron configuration is because it's different than what is expected for that balanced electron configuration. So take for example like palladium, right? So palladium, one may expect it to have 2 electrons in the 5s orbital and 8 electrons in the 4d orbital. However, this is not the case because there are 10 electrons in the 4d orbital and 0 electrons in the 5s orbital. So therefore we make that electron configuration green. Now if you want to know the actual reason why palladium has 10 electrons in that 4D shell but has no electrons in the 5s shell, it's simply because a half or fully filled subshell is more stable. So that's simply palladium trying to achieve more stability. So let's go on. Next, we'll consider the various divisions of the periodic table. So our 3 main divisions that we'll need to know are blocks, periods, and groups. So blocks reflect which type of orbital group is filled last. So for example, oxygen is in the p block because its 2p orbital is filled last. Then we move on to periods, which are just the rows on the periodic table. Or they're based on the principal quantum number, n, of the most recently filled s orbital. And groups are quote-unquote columns on the periodic table, but they are also indicators of the number of valence electrons for an element. So that's something useful to know when considering group numbers. Now, let's go back to that first periodic table image. You can see that hydrogen and helium are kind of floating here, along with the lanthanides and actinides. So we're going to give an explanation for that in a bit. You can see that hydrogen and helium are kind of floating, and so are the lanthanides and actinides. So we need to give an explanation for that. So let's first start off with hydrogen and helium. So if we're talking about the placement of these 2 elements in terms of electron configurations, if we attach hydrogen back to the entire periodic table, that would actually make sense because it's in the s block, and of course, hydrogen has 1 electron in the 1s orbital. However, if we attach helium back to that periodic table, then that would imply it's part of the p block, which is inferred through visual effects. Which is not true because the helium atom only has its 2 electrons in the 1s orbital. So that's something that you need to know about hydrogen and helium and why it's placed that way. Now, of course, we also have the lanthanides and actinides, which will be discussed next slide. So, in some versions of the periodic table, lanthanides and actinides are placed differently than some other versions. So in some versions, lanthanum and actinium is squeezed right in between the s block and the d block snugly. However, in other versions, both lanthanum and actinium are just placed in that f block region, which is below the rest of the periodic table. Now, going from that point, the electron configuration of many elements is especially important because that will allow us to predict whether an element can form singly or doubly charged ions. Not positive, not negative, just charged. So now we're going to go back to orbital energies. So back in chapters 4 and 5, we discussed about how the energy of atomic orbitals, especially when making molecular orbitals and molecules, are super important because of course they form the molecular orbitals as through, like how. Now, we established a few postulates back in chapters 4 and 5. And in those chapters, we said that there must be a meaningful contribution between 2 orbitals when making a molecular orbital. And a stronger interaction is formed from them being more equal in energy. So, we do have something to consider here, because especially with the molecules that are not homonuclear diatomics, right? Like hydrogen fluoride, hydrogen chloride, or like lithium fluoride, those atomic orbitals will be different in energy. So you have to consider how those energies will affect the shifting of the energies of the molecular orbitals. Now, going from there, back in chapter 2, we introduced the concept of what screening is. So, screening is basically a phenomenon where the inner electrons act as a kind of shield, and that reduces the attractive force between the outer electrons and the positively charged nucleus. So, people have then introduced the concept of an effective nuclear charge, which is basically like, what are the outer electrons actually feeling because that concept of screening is present. And also right here are the energies of various atomic orbitals through the elements. We need to explain the concept of screening. So, basically, if you can name 5 Italian brain rot terms, but can't explain an example of screening by the end of my lecture, then honestly, you're cooked, bro. But, if you look at the atomic orbital energy chart, you'll find something interesting. That the energy of the 4s orbital gradually decreases along the first set of the transition metals. So we'll go back to that one. You can see, as you go along these transition metals, the energy of the 4s orbital kind of just gradually decreases. But if you compare that to something like the 2s orbital or the 3s orbital, those energies rapidly decrease. Now, the reason for this, we can attribute it to the adding of electrons in the 3D block. And those electrons in the 3D block kind of screen or just kind of act as a shield for those 4s electrons. So that's why we can see somewhat of a gradual decrease in the energies of the 4s orbital. And in addition, this phenomenon is not seen with a decrease of orbitals such as the 2s and 2p orbitals. So next we're going to talk about the effective nuclear charge. So remember back when we had that equation for the orbital energy, right? So what we said is that the energy of an orbital with the principal quantum number n is equal to the negative of the effective nuclear charge squared times the Rydberg constant over n squared. So using a complicated method known as algebra, we can rearrange that to form that the equation for solving the effective nuclear charge is equal to the square root of the negative of n squared times the energy of the orbital over the Rydberg constant. Now, here's something to know. If an electron in an atom is perfectly screened by the rest of the lower electrons, then the effective nuclear charge is just 1. However, this is the real world and it's not a simulation. So of course, ZF will increase as the shielding effect becomes less perfect. Now, how we actually calculate those effective nuclear charge values, so the most accurate way to calculate those values are known as the Clementi values. Now, unfortunately, I can't go into how they're calculated because this monstrosity right here is too much to explain in a time frame that I can manage. All you need to know are that the Clementi values are based on quantum mechanics and they use some complex quantum mechanic math to calculate the effective nuclear charge. So next we're going to go over another set of rules that are used to calculate the effective nuclear charge. So these are known as Slater rules. And here's the first part of how this works. So we group orbitals like this, okay? So we put 1s into its own group, 2s and 2p into its own group, 3s and 3p into its own group, 3d on its own, 4s and 4p grouped together, 4d and 4f in separate groups, and so on. So basically, what we can infer is that the s and p orbitals that have the same value for the principal quantum number are grouped together, while the d and f orbitals are grouped separately. So the value of the effective nuclear charge is calculated as the atomic number minus s, where s is a shielding constant. And to calculate the value of s, you have to focus on a particular electron in an orbital group. And then you have to apply the rules that will be outlined in the next slide. So here are Slater's rules. I'm not going to make you memorize all of these, but simply, if we consider an electron in some shell, then there's no contribution to s from electrons in groups to the right of the one being considered, right? Because that concept of screening, that's only for electrons in groups that are below that electron that we're considering. So that's pretty logical. Now, a contribution of 0.35 is added to S for every single electron in the same group as the one that's being considered, except in the 1s group, where the contribution is 0.30. Now, in addition to that rule, if the electron being considered is in an ND or NF orbital, then all electrons below it in energy contribute 1 to S. Then we're going to look at how the effective nuclear charge changes across the periodic table. So we have two values here. So we have the Slater values, and then we have the Clementi values. So of course we know that the Clementi values are much more accurate than Slater's. And of course, these values are calculated for the outermost electron. Here's the trend in effective nuclear charge. So across a period, the Clementi values increase along a period for the highest energy electrons. And in addition, those values also increase as we go down a group. If we're talking about general trends, like between Slater values and Clementi values, we kind of get the same general trend, that if you go down a group, then the effective nuclear charge will increase, and you go across a period, the effective nuclear charge will also increase. So that's the general trend that's established by both values. Now, there are a few differences in the two values trends. So for example, if we descend a group, and then up to period 4, those Slater values will increase, but then they stay constant as we go down the group. And groups 1 and 2 are an exception. As for these, the effective nuclear charge remains constant from period 3 onwards. So I'll show you. So you can see with these Slater values, let's look at group 1 for example. So lithium's effective nuclear charge is 1.30, sodium is 2.20, and then from sodium it's just 2.20, 2.20, and so on. So that's something that you need to watch out for, especially. And in addition, now we're looking at the variation in orbital energies as we go down a group. As shown in the diagram, even though we know that the effective nuclear charge increases, which would infer that the orbital energies would decrease, there's somewhat of a gradual increase in orbital energies. What we're looking back at that orbital energy equation, right? And we can see that there's some kind of dependence on the term -1 over n squared. So as we descend a group, n increases, and overall this term starts to become less negative. So that leads to the positive trend as shown with the energies of the atomic orbitals. Anyways, we have our first occurrence of the second period anomaly. If we look back at the orbital energies, like say for example s orbital energy in group 16, right? We can see that there's still somewhat of a gradual increase as we go from sulfur to polonium. But you can see from oxygen to sulfur, there's an extremely sharp increase. This can be easily explained by looking at that -1 over n squared term. So if we increase n from n equals 2 to n equals 3, there's of course going to be a super sharp increase as seen in this graph right here. You can see from 1 to 2, there's a much sharper increase than, take for example, like 3 and 4. So that's an explanation for why the orbital energies rise so sharply. Now we have to look at the effect of what the D block does on the effective nuclear charge. So, in the image of the orbital energies of group members that I've shown you, there's somewhat of an interesting trend that is present. So if we look at groups 1 and 2, there's a gradual increase in the energies of the orbitals, which you cannot find in the groups from group 13 and after. And when going from aluminum to gallium in the energies of the NS orbital, there's a sudden downward jerk from going to aluminum to gallium, which we'll explain in this slide. So let me pull that up in the chart. You can see there's somewhat of a decrease when we look at aluminum to gallium. So we need to explain that more importantly. This is simply because if you look at the periodic table, in that electron configuration of gallium, there are 3d electrons being added. And the effect of those extra protons being added from aluminum to gallium has not had its full effect on the energies of the s and p orbitals, due to those 3d electrons being added to the electron configuration. So that's our explanation for that sudden downward jerk from aluminum to gallium. Now we've mainly talked about, somewhat of lighter elements. But what if we go on to heavier elements? What happens when we get to that point? So right here is an image of what seems to be orbital energy and the heavier elements. So you can see like 5s, 6s, 5p, 6p. Those are where the heavier elements reside. So we need to figure out what happens there. As shown in the graph, the energies of the 6s orbital for the transition metals that have it filled like osmium are lower than the energies of the 5s orbitals. So let's see this. So you can see that the 6s orbital energies are lower than the 5s orbital energies. So why is that? So we know that if we go down a group and we look at, that same S block, then generally there's going to be an increase in the energies, but for some reason there's that decrease. So one cause for this is the addition of 4 F electrons, which lead to a very slight increase in the effective nuclear charge felt by 6s electrons. And in addition to the addition of 4 F electrons, relativistic effects also come into play, especially in the heavier elements. Now, let's go back to the equation of orbital energy in a 1 electron atom to explain these relativistic effects. So, the energy of some atomic orbital with principal quantum number n is equal to the negative of the Rydberg constant times z squared, which is just the atomic number squared, over n squared. Now, see how we don't have to use ZF, the effective nuclear charge. That's because we're only accounting for that attractive force between that singular electron and the positively charged nucleus. So, because it's only 1 electron in there, we can just use Z instead of ZF. So, what if we try rewriting the Rydberg constant into terms of more fundamental constants instead? So, now, using the definition of what the Rydberg constant is, the energy of an atomic orbital is equal to this mass, right? So we can see there's an ME term. So ME is just the mass of the electron. And there's this E0 term. That's just the vacuum permittivity, also known as the permittivity of free space. And this E term is just the fundamental charge in coulombs, and H is just the Planck constant. So, what this equation shows is that the orbital energy depends on the electron's mass. Now, in hydrogen, the velocity of the 1s electron moves at 1 over 137 of the speed of light, which is, of course, very fast. Now, the main point I want you to take away from this equation derivation is for a 1 electron atom, that electron moves at a speed of c over 137, the speed of light. So, some people have inferred that if we reach that point where we have a 1 electron atom, and there are 137 protons in the nucleus, then it's simply impossible. It's been called Feynmanium because Feynman proposed that any atom that has this number of protons just wouldn't be possible because the speed of light is just, the universal time limit. Now, of course, there are some other studies that actually found online that kind of debunk this using some complicated math techniques. But anyways, let's go on to the relativistic mass of the electron. So, we're going to mention our most beloved scientist, Albert Einstein. So, in his theory of relativity, he stated that the mass of some object moving at a velocity v would be related to its rest mass by this equation. So, the mass of the object moving is equal to the mass of the object at rest over the square root of 1 minus the velocity over the speed of light squared. The 1s electron that's present in Mercury, which has an atomic number of 80, travels at approximately 58% the speed of light, and also has a mass that is 1.23 times the rest mass. Now, the reason why we're considering the mass of these electrons moving is important because the Bohr radius, which is basically just the most probable distance from the nucleus that you can find an electron depends on that mass of the electron. And it can be shown in this equation. So it says that the Bohr radius is equal to the free space permittivity times the Planck constant squared over the mass of the electron, which will change. And you also have that times pi times fundamental charge squared times z, which means that as z increases, since for the 1s electron, the most likely place to find the electron is at the Bohr radius, we can say that it contracts actually because of these relativistic effects. Now, this also leads to an expansion of the valence d and f orbitals in these heavier elements. Now, keep in mind that the relativistic effects, especially with heavier and heavier elements, amplify more once you get there. So that's something that you'll need to consider, especially throughout this entire chapter. So next we're going to talk about the Pauling scale of electronegativity. So electronegativity is kind of a vague term. And when you see it used across just like common speech, then you don't really know that definition. It's kind of difficult to quantify just because of its vagueness. Now, what Linus Pauling, the guy who won 2 Nobel Prizes, defined it as, he defined electronegativity as the power of an atom when in a molecule to attract electrons to itself. So, what Pauling did to try to quantify electronegativity is to use bond strengths. So, what he did is he used this equation right here. I'm not going to read it all out loud, but just know that the bond strengths affect the electronegativity of various elements. And in addition, the difference of those electronegativities of 2 elements squared is multiplied by some constant c. And Linus Pauling explicitly chose this constant c so that the electronegativity of fluorine, which we know now is the most electronegative element of all time, would be equal to 4. In his later works, he decided to make the constant equal to 3.98, but still it's very close to 4. So, using that Pauling electronegativity scale, this man was able to quantify electronegativity across the periodic table. And we use things like electronegativity differences to tell if a bond's polar covalent, nonpolar covalent, or ionic. Now, going away from that Pauling scale of electronegativity, there are many other scales, such as the Albrecht-Rauchow scale and the Mulliken scale, and these are based on different properties of an atom. So, there's going to be somewhat of a correlation between electronegativity and orbital energy. So, of course, electronegativity is often utilized to predict how polar a bond is, with the most electronegative element in a polar bond possessing a partial negative charge, especially with something like water. An actual understanding of bond polarity can be attributed to how atomic orbitals form molecular orbitals, as back in chapter 4. Now, it turns out that there's a strong correlation between orbital energy and the Pauling electronegativity values of various elements. So, you can draw a line of strong fit between data points that have X values based on the weighted average of the orbital energies of S and P valence electrons in your main group elements, and Y values of the Pauling electronegativity values. So of course I can't just say that the graph looks like this, I actually have to show you this. So right here is the graph that you'll be looking at. So you can see minus the weighted average orbital energy of S and P valence electrons and electrovolts and Pauling electronegativity. You can see that, yeah, you can draw a line of strong fit here actually. So that's something neat to know about Pauling electronegativity values. And just how, in my opinion, how impressive it is that this man was able to quantify electronegativity in such a way. So anyways, going back from the effective nuclear charge trenches, the relativistic trenches, and everything else, we look at atomic sizes across the periodic table. What we want to focus first on is the radial distribution function, which shows how much an electron is spread out across different distances from the nucleus. So, because it's kind of fuzzy, right? Because it's a distribution, talking about the actual size of an orbital or an atom for that matter is going to be hard. Now, Some people might just say, oh, you can just grab a molecule with that atom in it, like O2, F2, and then the distance between those two atoms is simply twice the atomic radius. But then, there comes that issue of allotropes. Like, for example, sulfur has monoclinic, rhombic. There's so many allotropes across different elements. So, which one to use is kind of hard because there are many different sources for what the atomic radius could be. And in addition, the phase of that element also is important. Gas phase, solid phase, liquid phase. What are you talking here, man? So, we need to find some way to derive the atomic sizes using some simple model. Now, what chemists use to find the atomic radius, this is just an extremely simple model, is that the atomic radius is equal to the Bohr radius times n squared, n is the principal quantum number, over the effective nuclear charge. And you can see in this graph right here, it actually kind of fits well with the experimentally determined data. You can see for at least most of the graph, there's somewhat of a general trend, a general fit with this model and the experimentally determined atomic radii. And right here is just a table of every single atomic radius that has been experimentally determined. Now we have to look at trends in the periodic table. So, as shown in the past image, the atomic radius seems to actually max out once we reach an alkali metal. And across a period, it starts to steadily decrease until we reach the noble gases. And this could be attributed to an increase in the effective nuclear charge. However, the effect of increasing that principal quantum number n is more significant than the increase in the effective nuclear charge. So that is a trend across the periods of the periodic table that you'll need to know. So, next we want to talk about something a bit weirder. So, especially in this chapter, the two main anomalies that you're going to be looking at are the heavier elements and second period. So we're going to look at the heavier elements here. So, it's kind of hard to predict the atomic radius change as you go down a group, especially with changes such as n squared and the effective nuclear charge. So, for example, the atomic radii of the third row of the transition metals almost match the sizes of the elements in the second row of the transition metals. So it'll be kind of hard to predict that. So, these elements must have their increase in the effective nuclear charge and a relativistic contraction of the 6s orbital, somewhat balancing out the increase in n. And relativistic effects start to become more important as we descend a group of the periodic table, which can explain why some members of a group are smaller than the ones that have come before it. So if we look at our heavier elements, right, there's going to be some kind of decrease maybe, or some kind of stagnation that could be explained due to these relativistic effects. So next we're going to consider the size, the overlap of atomic orbitals, and how that affects bond strengths. So when looking at the size of atomic orbitals, it's important to know the sizes and how they contribute to bond strength, and how overlap will of course contribute to bond strength. So, except for hydrogen, every single element in the first group exists in a metallic state. However, they can still form diatomic molecules, each of them having a sigma bonding and a sigma antibonding molecular orbital, with 2 electrons in that initial sigma bonding molecular orbital. So, from the graph, one may conclude that the overlap integral of the ns orbitals in the group 1 diatomic decreases as you go down. Now remember, back in chapter 2 I mentioned that the overlap integral is simply you take the product of two wave functions and you take the integral of that. And the greater the overlap integral, the more overlap that's present between those two atomic orbitals. Now we're going to go over some trends in ionization energy. So, the ionization energy is the amount of energy that a gas phase atom must absorb, and remember, the gas phase atom is isolated, and that atom must absorb that amount of energy to discharge an electron. So, the ionization of energy of an element gradually increases due to an increase in the effective nuclear charge as you go along a period. However, if you go down a group, the ionization energy of the element decreases because you ionize electrons in subshells that have a higher principal quantum number. And because they have that higher value of the principal quantum number, they're farther away from the nucleus, so it'll be easier to ionize. However, keep in mind that this decrease can level off at times. So it's easier to ionize an electron from the oxygen atom. From the nitrogen atom, this is an exception, because of the electron-electron repulsion that's present within that orbital of that 2p orbital in the oxygen atom. I accidentally put 2px. I think it should be 2py for the oxygen atom. So those are some of the trends in ionization energy. So across a period, increases. Down a group, decreases. But if you're going from nitrogen to oxygen, just keep in mind of that exception, that oxygen has a lower ionization energy due to electron-electron repulsion. And here's a graph of first ionization energy. So as expected, since the noble gases are so stable with their fully filled subshells, they all have the highest ionization energies. So this is the first ionization energy. So helium actually has the highest ionization energy, and yeah, that's because it's a noble gas. And in addition, those 1s electrons are super close to the nucleus. So it's going to be hard to ionize an electron from there. So we're going to go back to the heavier elements, and we're going to talk about first ionization energies in relation to these heavier elements. So, when looking at the graph of the first ionization energies of elements that are in group 1, you can see something that's kind of contradictory to that trend that's first established. So if you look at it right here, going from lithium to cesium, the experimental ionization energy decreases as expected, but if you go from cesium to francium, somehow this increases. So we need to find some reason for this experimental ionization energy, and that's because, no wonder, relativistic effects on the 7s orbital of francium lowers the energy of that 7s orbital. And in addition, from looking at the graph, you can see that if you calculate the ionization energies and consider relativistic effects, as you go into the heavier elements, those calculated ionization energies will match with the experimental ionization energies. So you have to calculate those relativistic effects, especially once you reach into the heavier elements. Anyways, we have a second period anomaly, another second period anomaly, so we're going to have to look at that. So, if you look at this graph right here, you can see that for second period elements like boron, carbon, nitrogen, those ionization energies will be much larger than the elements that are in period 3. So how can we explain this? So, the larger ionization for the period 2 elements is, of course, because of, N being smaller and the 2s and 2p orbital energy being much lower. And in addition, if we look at the transition to ionization energy between period 3 and period 4, it's kind of gradual, and that's because you fill the d electrons in between period 3 and period 4. And when we look back at the second period, we can see that a larger ionization energy for many of these second period elements indicates that we won't be able to form these natural cations. So rarely do you ever find a nitrogen cation, in nature. And that's because of that super high ionization energy. Next, we're going to learn some thermodynamics, which is everybody's favorite. So first, we're going to define what the electron attachment enthalpy is. And so basically, this is the change in enthalpy from adding an electron to an atom. So our general reaction can be represented as X, which is some kind of atom in the gas phase, and then you add it with an electron in the gas phase, and you get X minus in that gas phase still. So that's our general reaction to determine what the electron attachment enthalpy is. Now, the electron affinity is actually defined as the negative of the electron attachment enthalpy. Now, from this definition of the electron affinity, it's easy to tell that as that electron affinity increases, the more favorable it is to attach an electron to an atom. However, if we're looking at trying to determine the electron affinity for an element, there's somewhat of a larger margin of error if you're trying to determine that directly. And most of the times, you just have to resort to indirect methods to measure the electron affinity. So here are the electron affinity values for elements across the periodic table. So you can see for the noble gases, that electron affinity is 0, which indicates that no, the noble gases don't need an electron added to them. But if you look at something like the halogens, right? The halogens are known for being down bad for an electron, right? They're super reactive, super corrosive, and that's because they just want one more electron to achieve that noble gas configuration. And so that's why the electron affinities are so high. Now, here's something interesting. You would expect fluorine to have the highest electron affinity, but chlorine actually has it, so we need to explain that first. The reason why chlorine has a higher electron affinity than fluorine is mainly attributed to how small the 2p orbital is. We also have to consider the effect of filled and half-filled subshells. So if you try to add an electron to an atom that has a half-filled or filled shell / subshell, you'll yield, a not so favorable interaction. So take, for example, zinc, which has a filled electron subshell. As you can go back, zinc has a full 3d electron subshell. So therefore that electron affinity will be, around 0. Or for that matter, take the transition metals that are present within group 7, such as manganese and technetium. Now, they have these half-filled subshells, these half-filled Nd subshells. So that's why electron affinity is so low for group 7 transition metals. And this example of group 7 can also be found in group 15. So if we look at group 15, there's that half-filled Np subshell. So take for example something like nitrogen or phosphorus. It's lower than the rest of the elements in the p block on their period. So anyways, let's ignore those past exceptions of elements that have filled or half-filled electron shells and subshells, and let's just look at the general trends. So there's a general increase in electron affinity as you go along a period, if we don't consider those edge cases that much. So another way to phrase this to say that as you go along a period, both the electron affinity and the effective nuclear charge increase. So it's not surprising to say that the halogens have the highest electron affinity out of all the groups in the periodic table. As I've said, they're so down bad for an electron. That's why the electron affinity is just so high for them. And interestingly enough, the element that has the next highest electron affinity other than those halogens is gold, which can form the auride ion, Au-, and it can be found in salts such as cesium auride. I kid you not, that actually exists. Anyways, we have another second period anomaly, of course. So, one interesting feature of the electron affinities of various elements across the periodic table is that the electron affinities for elements in period 2 are less than expected by calculations for the expected electron affinity. So, one reason for this is simply because the small sizes of the period 2 atoms and their orbitals are the reason why there's such a small electron affinity than expected. And in addition, adding another electron will lead to more repulsion, and this in comparison to period 3 elements. So, overall, small sizes of second period atomic orbitals lead to that drop or kind of unexpected electron affinity. Now, we introduced what oxidation states were back in chapter 1, and this will be useful once we enter electrochemistry at the end of this book. So, the highest oxidation states are shown once an element is bonded to either fluorine or oxygen. Now that's because fluorine and oxygen are the most down bad for electrons. Or, in other words, you can just say that they're super electronegative. Now, in addition, the reluctance of NS electrons in the outermost shell in heavier elements to participate in bonding is known as the inert pair effect. And this is another heavy element kind of a rule that you'll have to follow. So right here is an extremely massive table of every single oxidation state that an element can have. Now, the most important oxidation states are highlighted in black, and the lesser important ones are in blue. So, here's just an overall summary of what we've covered. So, the energies of orbitals follow a fairly regular pattern across the periodic table as we go down a group and we go across a period. And in addition, understanding trends and effective nuclear charges can give us an alternate perspective on different periodic trends. So generally, the effective nuclear charge increases across a period and down a group. In addition to understanding the effective nuclear charge, understanding why orbital energies vary in the way that they do give a sense and understanding other trends in the periodic table, such as the sizes of orbitals, ionization energies, and electron affinities. In addition, atomic sizes generally decrease across a period and increase down a group. Now, our main two anomalies that we've covered this entire chapter is that the period 2 elements often have different properties than expected, and especially with heavier elements, relativistic effects need to be taken into account when trying to rationalize their properties. So next we're going to talk about the sizes of orbitals. So since in this chapter we're going to be talking about the bonding in elements, there's no need to talk about the relative energies of the valence orbitals because they're perfectly matched. However, it is still important to consider the size of orbitals. So, the elements in period 2 have stronger overlap between valence orbitals, which leads to stronger bonds. So, generally, as you move down the periodic table, bond strength will decrease due to that lesser overlap from larger atomic orbitals. And this is considering normal bond lengths. So next we're going to talk about numbers of electrons. So remember that the strength of bonding is affected by the distribution of electrons within these antibonding and bonding molecular orbitals. So, of course, the more electrons in bonding molecular orbitals, the stronger the bond. If we do a throwback to period 2 homonuclear diatomics, then nitrogen gas, looking at our molecular orbital perspective, will have the strongest bond. Because if you look at the MO diagram, it only fills out those bonding orbitals formed from the 2p orbitals. Now, diatomic boron and carbon will have fewer electrons, so not all the bonding orbitals are filled. And diatomic oxygen and fluorine fill up anti-bonding molecular orbitals, which weaken the bond. Now, if we move on to 3D structures, where group 14 elements like carbon perfectly fill all bonding molecular orbitals within that 3D structure, that can explain why the enthalpy of atomization, which is basically just a measure of how strong a bond is the highest. And you can see right here the enthalpy of atomization. So for group 14 elements, there is going to be a higher standard enthalpy of atomization. So let's go on to elements in group 14. So the structure of the diamond form of carbon is shown above, right next to the title. And every single carbon atom is sp3 hybridized, and they have thus a tetrahedral arrangement, which means that if you have n carbon atoms, then they form 4n molecular orbitals, where all the bonding molecular orbitals are filled. Now, in addition to that, all elements in group 14 have an allotropic structure that's similar to this diamond structure, except for lead and beta tin, which have different structures than the diamond structure. So moving to another group, group 15, because they contribute 5 valence electrons instead of 4 valence electrons as compared to group 14 elements, there's going to be one lone pair on every single atom. We have 5 n valence electrons contribute to molecular orbitals, so there will now be n valence electrons that occupy antibonding molecular orbitals. Now, we know from chapter 5 that we can think of a lone pair as the canceling out of electrons in a bonding molecular orbital and an anti-bonding molecular orbital. So that explains why we have one lone pair on every single atom. Now, excluding nitrogen, group 15 elements have allotropes that all form 3 bonds and have a lone pair on each atom, just throughout the entire 3D structure. Now we say excluding nitrogen because, nitrogen is a gas, and it does not form these 3D structures normally. So next we'll move on to group 16. So again, using a molecular orbital theory approach, there are going to be more electrons now in those antibonding molecular orbitals, which now means that we have 2 lone pairs on every single atom when we're looking at 3D structures. So we look at something like sulfur. There are 2 main allotropes that you need to know: rhombic and monoclinic sulfur. So they have 8-membered rings with 2 bonds, 2 lone pairs per atom, and these rings are formed in different arrangements if you're looking at either rhombic or monoclinic sulfur. Now, in addition, selenium also exists in a range of forms, including rings, while tellurium includes network spiral chains in their 3D structure. That's group 16. So anyways, if you look at group 17, for each atom, there will only be 1 bond formed and 3 lone pairs that are formed, because we're adding even more electrons into antibonding molecular orbitals. So take, for example, the structure of iodine. You can see they're just diatomic molecules that are held together with London dispersion forces, which are just an intermolecular force that's present in every single molecule. But finally, we're going to look at just one more second period anomaly. So, when we look at the second period, it's interesting because once we take the case of nitrogen and oxygen, they naturally occur as diatomic gases instead of solids with rings. So we have to consider why this happens. So let's take one example: diatomic fluorine gas, which somehow has a bond weaker than diatomic chlorine and bromine. So, molecular orbital theory states that the antibonding molecular orbital is much higher in energy because there's going to be more overlap, which is much larger in fluorine due to the smaller size of its 2p orbitals compared to 3p orbitals. So, the effect of antibonding orbitals is not only do they cancel out some of the pi bonding, if we're talking about electrons filling pi antibonding molecular orbitals, they not only cancel out some of the pi bonding, but also some of the sigma bonding that will occur. So this is known as the antibonding effect. So, the energy difference of the supposed energy of the pi antibonding orbital and the actual energy is the energy difference. And because fluorine has that greater degree of overlap compared to something like chlorine gas, that energy difference will be much larger, making that bond weaker. In addition to the anti-bonding effect, we also have something known as the lone pair effect. So basically, what we're saying here is that the degree of repulsion from lone pairs is greater in diatomic fluorine than diatomic chlorine. Now, if we go back to our MO diagram of fluorine, then we can't really see any lone pairs, because as said in the MO theory chapters, lone pairs are just thought of electrons canceling each other out with the electrons both in antibonding and bonding molecular orbitals. And as said in the last slide, the pi antibonding molecular orbitals in fluorine gas cancel out the bonding more than diatomic chlorine gas, which is the origin of this model. And honestly, having these two approaches is super wild, considering that we're just asking why the second period does not form these solids. Going on to p-block diatomics, the trended bond strengths formed in these p-block diatomics can be explained by the anti-bonding effect, especially with oxygen and fluorine compared to sulfur and chlorine. So, of course, the anti-bonding effect is, of course, there's going to be more cancellation of bonding by filling up those pi antibonding molecular orbitals, because the degree of overlap is just much larger. So we can just use the anti-bonding effect to explain bond strength in p-block diatomics from here. So next we're going to go over nitrogen and oxygen. So we can now have an actual view on why oxygen and nitrogen do not form structures that contain rings and chains, like sulfur and phosphorus. So let's take that first example of the chain of oxygen atoms that are all sp hybridized. So you have 2 lone pairs and 2 pi bonds per oxygen. So we're just assuming that there's going to be some kind of chain. So the reason why we don't find this is, simply put, that lone pair repulsion would be too much. Or if we can explain this using band theory, we will have a partially filled band, but we also have anti-bonding crystal orbitals that are filled. So therefore the structure would be unstable because we have those anti-bonding crystal orbitals filled. And for the same reason, nitrogen cannot form planar sheets. However, carbon, because it does not fill in those anti-bonding orbitals, is much more stable than oxygen and nitrogen. Next, we're going to finish off with an introduction to metallic structures. So, most elements on the periodic table are metals, so it's crucial to understand what's going on with their structures. So, the key feature of each metallic structure is that we're going to look at the number of bonds that are associated with each atom. Now, when we mean bond, we just mean the number of nearest neighbors that each atom has in the situation. So, most metals adopt hexagonal close packed, cubic close packed, and body-centered cubic. So those are your three main structures that you need to know. HCP, CCP, and BCC. So first we're going to look over close packed structures. So we can talk about the various structures of metals by talking about how round objects such as spheres can stack in space. So if we have one layer of spheres, then the closest possible packing of this one layer will have one sphere touching 6 others. They will fit over the holes of the first layer. So congrats, you now made a close packed structure. Now it depends on where you place the resulting layers on as we keep going on with more and more layers, as shown in the first image. Because if we consider our layers and their arrangements, there's going to be somewhat of a difference when looking at hexagonal close packed and cubic close packed. Now, hexagonal close packing is adopted by magnesium, titanium, and cobalt. And overall, this is one of the most efficient forms of packing, if not the most. So in this packing arrangement, the structure repeats every third layer, as seen in the last image, and we can label the packing pattern of the layers as A, B, A, B, because that structure repeats every third layer. So next we're going to go over cubic close packing. So this cubic close packing structure has layers that repeat every fourth layer. So we can represent it as ABC, 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 so on. And the structure is also known as face-centered cubic. So we went over cubic close packing and hexagonal close packing. Here's another structure that you need to know, known as primitive cubic. So it's not as efficient as close packed structures, but quite frankly, every single layer is the same as every other layer spatially. And atoms are just at the edges of every single unit cell. So what a unit cell is basically just, what if we took a crystal and we took the simplest part of it and we represent that 3D arrangement using just the most simple way that we can think of. So we just have a square layer and we just stack the square layers on top of each other. Another structure that you'll need to know is body-centered cubic. So in its unit cell, there's one whole atom in the middle of the cube with 8 1/8 of other atoms in the corners. Overall, 68% of the space is occupied, which means that this is more effective in packing than, take for example, primitive cubic. We're basically just going to end this off with bonding in the metals. So remember back then when we considered the structure of elements in the P block and how stability can be affected by bonding within these elements. So now we're going to consider these transition metals. So we considered how atomic orbital overlap and how many electrons get donated to various molecular orbitals affect stability. So let's consider the enthalpy of atomization of period 6 metals. So now we're forced to consider how d orbitals bond too. Now, imagine for a moment that we get bands overlapping. So as you move across period 6, the bonding molecular orbitals get filled until tungsten. So tungsten has the most electrons in these bonding molecular orbitals, or bonding crystal orbitals if you're taking that band approach. And after that, we have anti-bonding molecular orbitals filled. So you can see that's why generally tungsten has the highest enthalpy of atomization. Now, we're mainly going to end this chapter off with the transition from metals to nonmetals. So one interesting feature of the periodic table is the division between metals and nonmetals. So the book classifies the periodic table as having 4 main classes of metals. So metals have delocalized bonding with around 8 to 12 nearest neighbors, and in addition, the presence of partially filled bands allows for the conduction of electricity. Now, semi-metals are poorer conductors of electricity compared to true metals, and each atom also has fewer nearest neighbors. Now, there's also a band gap, which I mentioned back in chapter 6. So increasing the temperature of some metals and semi-metals actually decreases that conductivity. Now, semiconductors also conduct electricity poorly, but have a small enough band gap, which is around like 0.1 to 4 electron volts, that allows for electrons to be promoted from the conduction band to the valence band. Now, nonmetals have more localized bonding and do not conduct electricity, and therefore are insulators. Now, we're going to look at more orbital size and overlap. So, when crossing a period, the effective nuclear charge increase, and the size of the orbitals decrease, meaning that there will be a trend of having fewer nearest neighbors and more localized bonding. So if we go down a group, those orbital sizes will increase, and thus there will be a trend of more of a metal-like structure, right? So take for example something like lithium. So they have many slightly longer bonds in the solid, and they give stronger interactions per atom than having a single closer partner in Li2. So just put simply, the solid allows for more bonding to occur and overall just more stability. So that's why lithium is solid instead of existing as a diatomic. However, this is not the case for hydrogen. Because the 1s orbitals are so small, it can only really exist as that H2 molecule. We're going to look at semimetals. So the transition from metals to nonmetals is more gradual across the periodic table, with both semiconductors and semimetals, which are also known as metalloids, bridging this transition. So the semimetals conduct like metals, but still have more localized features like nonmetals, like localized bonding. So if you go down the P block, for example, with any group, the structures that are present start to become more and more metallic. So take for example group 15. So the structures of arsenic, antimony, and bismuth show increasing similarity in atomic distances, with bismuth having a metallic coordination of around 6 neighbors. And under pressures, they adopt fully metallic structures such as alpha polonium. So similar trends occur in other groups such as the halogens. So like the ratio of intermolecular distances in solid chlorine, bromine, and iodine decreases down the group, showing that iodine approaches metallic bonding. So at high pressures, iodine even becomes metallic, which exhibits somewhat of a distorted close packing structure. So that's actually the end of this long lecture. I hope you enjoyed it no matter what. And of course, I'm going to end this off with Kurovac's quote. In the words of our King Kurovac, if you can't understand this, I advise going to your nearest primary school. Now, I will get you guys a sneak peek. So, Chapter 9 will then talk about bonding between the elements. So we're going to talk about size and energy of orbitals, how to classify compounds as either ionic or covalent, structural trends in the periodic table, the effect of radius in bonding, and certain compounds and the structures. Now, overall, that chapter kind of gets a bit shorter. So, expect the best